Dear students, continuing with our lecture series on medicinal chemistry. This is our third lecture on medicinal chemistry, and in the first lecture we have discussed about the basic concepts, and in the second lecture we have started with physicochemical properties of various types of medicinal compounds. And as I have already told you that medicinal chemistry is an interdisciplinary science, and the basic concepts have been explained in our first lecture, that is medicinal chemistry basic concepts. Then physicochemical properties, various types of important physicochemical properties, as I have already explained in the previous lecture, that is physicochemical properties 1. In the first lecture I have explained about hydrogen bonding and chelation. Now in this second lecture on physicochemical properties, we will be discussing about bioisosterism and surface activity through surface tension and other properties of the medicinal compounds. Now, bioisosterism, as has been defined by Friedman, basically is the phenomenon by which the compounds usually fit the broadest definition of isosteres and possess the same type of biological activity. So basically, meaning is that biological activity of any medicinal compound is dependent upon the type of compounds, and if some compounds they possess similar structure, then they will possess same type of biological activity. And these isosteres or bioisosteres, they are functional groups or molecules that have chemical and physical similarities, producing broadly similar biological properties, which means the same thing, that if the medicinal compounds they have similar chemical and physical properties, their biological properties will also be similar. So isosterism is very important to the medicinal chemist, because biological characteristics of isosteres appears to be similar, as I have already told you. Then more frequently than physical or chemical characteristics. So for example, if we see these three compounds, you will see that they have same functional groups, tertiary amine and ether functional group. This is ether functional group, this is also a tertiary amine. Only difference is in the structure of the tertiary amine moiety which is attached to the ether. Now if there is a compact substituent on the terminal nitrogen, then activity will be preferred. That compound will be having more activity. For example, if we compare these three, this tertiary amine is having a cyclic structure, whereas these two they have open chain structure, and this nitrogen is attached to two ethyl groups, whereas this nitrogen is attached to two methyl groups. And as I have told you that preference is for small compact substituents on the terminal nitrogens in case of antihistamines. So all these compounds they act as antihistamines. Now when experimentally the biological activity was determined, it was found that the analog one, this one, where the tertiamine is in cyclic structure, possesses twice the activity of 3. If we compare the biological activity, antihistamine activity, this compound and this compound, this is 2 times than this compound. Whereas it showed an activity that is many times greater than that of open chain diethyl amino. And if we compare the activity of this and this is better than this many times. So basically here small compact substituents lead to higher activity, and here cyclic structure leads to even higher activity than this NN dimethyl analog. So we can see that similarity in structure will have same type of biological activity, because all of these three they act as antihistamines. Now the isosteres or bioisosteres, they have been classified into two types. One is classical bioisosteres and other is non-classical bioisosteres. Classical bioisosteres, they have similarities in shape and electronic configuration of atoms, groups and molecules which they replace. So for example, say if we are having two compounds, in one of the compound only one group is replaced by another group which will have the same electronic configuration of atom, groups or molecules which have been replaced, and their structure, their shape also remains almost same. So then such type of compounds, they will be called as classical bioisosteres. And the biological replacement in design of a new target drug molecule is solely and significantly depend on the specific biological system under critical investigation. So basically, if we take some examples, for example, the classical bioisosteres, they can be formed if we say replace F by H or H by F, or OH by NH or NH by OH. So like this, these are all examples of monovalent atoms or groups which can be replaced or with each other, and such type of replacements which will be formed, they will have almost similar biological activity as that of its isostere. So for example, if you compare the activity of the uracil and 5-fluorouracil, you can see the structure of the molecule is same in both the cases, except that here hydrogen has been replaced by fluorine. So these are the examples of classical bioisosteres. You see this example, hypoxanthine and 6-mercaptopurine. Here, this part of the molecule, this structure is same, except that OH has been replaced by SH. So these also have the same type of or similar type of biological activity. Then folic acid and aminoterrin, if you see here OH is replaced by amino, rest of the molecule is same. So these two compounds, they also act as classical bioisosteres, where monovalent atoms or groups, they are involved in the replacement of one another. Then similarly, divalent atoms or groups like carbon sulfur double bond, carbon oxygen double bond, carbon nitrogen double bond and carbon carbon double bond, they may be involved in replacement of different types of atoms. For example, if we see this procane and procanamide. This is ester group and this has been replaced by amide group. Rest of the molecule is same in both the cases. So both of these, they are the example of classical bioisosteres. Then similarly trivalent atoms or groups or tetravalent atoms or groups, they can also act as classical bioisosteres. Then ring equivalents, they can also, like benzene ring can be replaced by pyridine ring. So here you can see carbon is replaced by nitrogen. Similarly here in this case sulfur is replaced by oxygen. So these two, they can act as bioisosteres and these two, they can also act as bioisosteres. So they are regarded as ring equivalents. Then non-classical bioisosteres, they are different from classical bioisosteres as they do not obey the steric and electronic definition of classical isosteres. And also they don't have the same number of atoms as replacement. So we cannot say that their structure is similar in both the cases, both the isosteres. So, although many of these functional moieties practically just behave as one, but they have one of the following characteristic which is present in that: their electronic properties may be same, their physicochemical properties may be same, their spatial arrangements may be same, and the functional group which is critical for the biological activity, that may be same. So either one or two of the properties may be similar, because of that they may have the similar type of biological activity, and such type of compounds which are not similar in shape and structure, they are called as non-classical bioisosteres. So for example, if you can see this these exchangeable groups. So if you see the structure of this compound and this compound, they are similar to each other, and here one of the hydroxyl group has been replaced by the sulfonamide. Methane sulfonyl amide group is present here in case of sotrinol, whereas this isoproterenol is having the hydroxyl group. So you can see that the chemical structure of this is different from this, that they do not obey steric or electronic definition of a classical isostere. So these two, they have similar biological activity, but they will be regarded as non-classical bioisosteres. Similarly, these two compounds, you can see that here this uh, aromatic ring is replaced by this aromatic ring, where one of the carbon is replaced by nitrogen, and here at the fourth position we are having hydrogen, whereas here we are having halogen. So there are two replacements which are there in these two types of compounds, and these are regarded as non-classical bioisosteres. Then estradiols and transdiethyl stilbestrol, you can see that here this is having a carbon-carbon double bond with phenolic moieties, whereas here this is a steroidal compound, but their activity is similar. So one is cyclic structure, other is non-cyclic structure, but these because of the similar biological activity, they are called as non-classical bioisosteres. Then these two compounds here, this is having a cyclic ring structure for the tertiamine, whereas this is having an open chain structure for the tertiary amine, rest of the molecule is same, so they will be regarded as non-classical bioisosteres. Then in these two compounds, here this is having a cyclic structure, whereas this is having a open chain structure or non-cyclic structure, but these will be regarded as non-classical bioisosteres. Then next properties is surface tension, and a surfactant is a material that can reduce the surface tension of water at low concentration. So we all know about the surfactants and surface tension as a phenomena, but the application of surface tension in medicinal chemistry is very important, because the surface agents, they can either increase or decrease the drug absorption, and we know that drug absorption is very important for a disease to be cured. So the increase or decrease of the drug absorption will depend upon the chemical nature of the surfactant which we are going to use as drug, or its concentration, or its effect on biological membrane and micelles formation, which what is the process of micelle formation, because here micelle formation is that hydrophobic and hydrophilic. This is hydrophilic, this is hydrophobic part of the surfactant. So the way they are arranged around the drug, that will lead to the formation of micelles. So when surfactant is having low concentration, then the absorption of the drug will be increased. So it enhances the absorption rate of the drug. Whereas at higher concentrations, the absorption rate of the drug will be reduced or decreased. So in low concentrations, they reduce the surface tension and bring about better absorption through better contact of molecules with absorbing membrane. But when the concentration crosses the CMC, that is critical micelle concentration, the surfactant aligns them at the surface so that the hydrophilic end towards the water and hydrophobic end is squeezed away from the water. You can see over here the hydrophilic end is towards the water and hydrophobic part is away from the water, right, towards the drug. So that is how this molecular aggregate is called as micelles, and these will entrap the drug molecule in their hydrophobic core, and because of that the drug will not be able to be absorbed. So this will result in retardation of the rate of absorption, or it reduces the rate of absorption, or it decreases the rate of absorption. Now the surface active agents which are used as drugs, they have been classified into four categories. Anionic surfactants, which are generally ordinary soaps or salts of bile acids, salts of sulfate or phosphate esters of alcohols, or salts of sulfonic acids. Whereas cationic surfactants, they are generally high molecular weight aliphatic amines or quaternary ammonium derivatives of these amines. Then non-ionic surfactants, they are generally polyethylene ethers, glycol esters of fatty acids. And amphoteric surfactants are that alkyl amidopropylamine N oxides, then alkyl dimethylamine N oxides, alkyl betanes, BT, and alkyl amidopropylbutane. So all these types of surfactants, they are called as uh, amphoteric surfactant, and we will see their examples one by one. Anionic surfactants, as you can see, they may be carboxylates, they may be stearates like this sodium salt, that is anionic. Then cholic acid and deoxycholic acids, they are the derivatives of bile acid. Then glucolic acid, ethoxylate, so these carboxylates basically polymeric. Then zonyl fluorosurfactant, again they are carboxylates. And then glycolic ethoxyloryl phenyl ether, so polyether containing carboxylate functional group. So all these types of surfactants, they are categorized under anionic surfactants, and they will, you will see that they have negative charge, that is anionic in nature. Then non-ionic surfactants are these Bridge 30, Trenton, X100, Tween 80, all these, they are commercially available. You can see that these are polyethylene ethers, and polyethylene esters as the surfactants. Then these are cationic surfactants. Basically, they will have positive charge on the nitrogen. Quaternary ammonium system is generally acting as cationic surfactants. And then these are the examples of amphoteric surfactants. They have both type of functional groups present, which may be non-ionic and ionic also, cationic also, and ionic also. All type of functional groups, they are present. For example, in this case, you can see this is having a cationic part also, an ionic part also, right? So this is having an ionic part also and non-ionic part also. So depending upon the structure of these, they can either act as anionic surfactants or non-ionic surfactants. Now, applications of different types of surfactants for different types of diseases has been achieved. For example, this benzalkonium chloride, we know, is a cationic quaternary ammonium salt, and this has been found to have bactericidal activity, and in many tubes or creams this is used. Then acetyl pyridinium chloride also is having this is the structure for acetyl pyridinium chloride. This also has shown the bactericidal activity, and these bactericidal activities are is because of the surface active properties of these molecules. Then antihelminthic activity of hexyl resorcinols. Resorcinols, you know, they are 1,3 or 1,2 phenols, 1,2 dihydroxybenzenes. So they have been reported to have this type of activity. So here the activity of these types of compound increases by low concentration of the soap and decreases by high concentration of the soap. Then there are highly surface active agents like ionic surfactants. They are not used internally but only topically as skin disinfectants or sterilizers for sterilization of instruments. Then non-ionic surfactants, they are largely employed in pharmaceutical preparation for oral use as solubilizing agents of water insoluble or slightly soluble drugs. Then surface active agents, they have also find application as central nervous system depressant drugs, such as sedative or hypnotic, anticonvulsant, and central laxant agents. And generally, the non-ionic surface active compounds, they have been found to be effective central nervous system depressant drugs. Then anionic and non-anionic surfactants, which have been used very effectively. One example is surfactant-based solution is Taxol. Taxol, we know, is a very effective anti-cancer drug, and this is used as a solution of chromophore, 50% solution of chromophore, where this Taxol is dissolved in the surfactant, and it is used as anti-cancer agent. Similarly, other drugs like valrubicin is also used in the used as a surfactant based solution of 50%. Then cyclosporine is also used as a surfactant based solution in 65% chromophore. So these are some of the applications of surface active agents. Then surfactant preparations, they are used as replacement therapy for treatment of premature infants suffering from neonatal respiratory distress syndrome. And then lung surfactant preparations, they have been used in combination with the supplemental oxygen and mechanical ventilator to facilitate the gas exchange. And important example is baractane, which is modified bovine extract, or calf actant, which is extracted from lungs of calves, or porcantin alpha, which is extract of porcine lung. So all these are the important surfactant preparations which are used for lung diseases. So this is the literature which is used for preparing this lecture. Thank you very much.